who is going to tell us about his research. With that, I would like to ask Francis maybe to introduce our speaker, if he desires so.
If you desire. Good morning, everyone. My name is Francis Aguas. I'm a second-year PhD student in Dr. Andrew Brown's lab here at the UCI Center for Translational Vision Research. And it's my pleasure to introduce today's speaker, Dr. Daniel Palanker. Dr. Palanker is a professor of ophthalmology and electrical engineering at Stanford University. He received his PhD in applied physics from the Hebrew University of Jerusalem, Israel, and postdoctoral training in physics, namely multiphoton imaging at Stanford University. Dr. Palanker studies interactions of electric fields with biological cells and tissues and develops optical and electronical technologies for diagnostic, therapeutic, surgical, and prosthetic applications, primarily in ophthalmology. In the field of electroneural interfaces, he is working on high-resolution photovoltaic retinal prosthesis for the restoration of sight and other implants for electronic control of organs. In the field of optics, he develops imaging of physiological signals for non-invasive and label-free imaging of neural signaling in vivo. Dr. Palanker's work has been well supported by multiple NEI R01 grants and has resulted in over 150 publications. He has garnered numerous recognitions in his career, including the SPIE Translational Research Award, Scientific Achievement Award by Alcon, and has been honored as an Arvo Silver Fellow. He holds over 70 issued patents, and several of his developments are in clinical practice worldwide, including the Medtronic plasma blade for precise cutting and coagulation of soft tissue, the pattern scanning laser photocoagulator or Pascal by Iridex, and the femtosecond laser cataract surgery or Catalyst by Johnson & Johnson Vision. With that, please join me in welcoming Dr. Palanker for his talk titled Photovoltaic Restoration of Sight in Age-Related Macular Degeneration.
Thank you very much for the introduction. I will share my slides. Can you see the slides?
Not yet.
Yes.
Yeah, it's all visible. Okay, perfect. All right, it's great to be back. Thank you very much for the opportunity to give an update. I think I spoke on a seminar just before COVID. I think it was February 2020 or so. And since then, we have a lot of exciting results in clinic and the new generation of the implant that we have tested in animals, and I'm going to share these results. So I'll start by disclosing my financial consulting relationship with Pixium Vision. It's a French company that commercializes our technology and takes it to clinical trials that I will actually present. The patents related to this technology are licensed from Stanford University to Pixium Vision. And I also want to start by acknowledging my excellent team at Stanford and our collaborators in Pixium Vision and a longtime collaborator, Keith Mattison from Strathclyde University, and our funding. So just a few words about retinal signaling and how we utilize it in prosthetic vision. So vision begins by hyperpolarization of photoreceptors under illumination. So these are non-spiky neurons, so this conversion is semi-linear in certain range, in about 2 orders of magnitude. And that affects the rate of release of neurotransmitters on a second layer of neurons, second-order neurons, also non-spiking, bipolar and horizontal cells, which perform spatial and temporal filtering, but they're still non-spiking gradient response neurons, so it's relatively easy to modulate the response by amplitude or by duration of the stimulus. And then information is transferred through the retinal network to ganglion cells, where it is digitized or converted into binary spiking patterns, and they are much more complex. The encoding now is spread over about 30 types of different ganglion cells, extracting different aspects of visual information from the scene or over overlapping mosaics, and encoding this in a spiking rate and number of spikes. And there are different types of ganglion cells I mentioned, not only on and off, but also transient, sustained, with different sizes of receptive fields and so on. So the further away we are from the origin, from photoreceptors, the more complex and distributed is retinal code, and more difficult is to reproduce it. And therefore, we decided to address the problem of reintroduction of visual information as early in the visual chain as possible by stimulating bipolar cells. So the disease we are treating is called atrophic AMD, or geographic atrophy, where photoreceptors are lost in the center of the macula, and patients lose sight, central vision, but the inner retina is relatively well preserved. You can see layered inner retina in the scotoma, and these patients primarily want a restoration of ability to read and recognize faces. An important feature of visual system in humans that the sampling of the visual field is very uneven. The high resolution is only in a very small central area, and the acuity drops with eccentricity rapidly. We are unaware of that because we compensate by eye scanning, but as soon as you lose central vision, you become acutely aware of this feature because patients cannot read, cannot recognize faces, so the high resolution vision is gone. The disease of AMD actually begins with loss of or dysfunction of retinal pigment epithelium, followed by the loss of photoreceptors. And our approach is to restore vision by reintroducing visual information, by replacing photoreceptors with photovoltaic array, and stimulating the second-order neuron, primarily neurons, bipolar cells in the retina, and relying on signal transmission through the retinal network, which preserves some of the features of the signal processing, as we'll see. So conceptually, if you look at this figure, instantaneously you see something like that. And in AMD, we are losing central vision. I'm showing in black here. It's actually not black, it's just missing. And then the idea is to overlay it with a central prosthetic vision, which is a grayscale, and with acuity that we hope to achieve 20 micrometer in patients. We have seen this only in rats currently. I'll show you what we've got in patients. And with 8 levels of gray, which is simulated here. Now, how do we hack the system? We apply electric field across the cells. Cells polarize because they're conductive inside and surrounded by non-conductive membrane. The depolarized side, where voltage is decreased, affects the conductivity of ion channels. Ions flow in, change the cell potential, and that affects the output. In spiking neurons, it will generate a spike. In non-spiking, it just will regulate their output of neurotransmitters on the next layer of neurons. So activation function is relatively simple. It's just voltage drop across the cell. One of the major limitations in electroneural interfaces is the transfer of charge from electrodes to electrolyte. It's limited by the fact that this interface is capacitive. So we cannot sustain constant current. And like it would be in normal vision, constant light should be converted into constant current. It's impossible because the interface is capacitive. And the way we deal with that is that we operate at high enough frequency of pulses, charge balance pulses, that flicker fuse. And so we, in bipolar cells, we apply electric field primarily vertically to create a voltage drop across bipolar cell and depolarize the axonal terminals of bipolar cells, where the voltage sensitive calcium channels are. They respond by opening, and that leads to the release of neurotransmitters onto ganglion cells, and that affects ganglion cell potential. So if we operate at low frequency, the polarization of a cell is very rapid, and basically we get pulsed kind of response, including pulse calcium influx and pump out. But if you operate at high enough frequency, because the calcium pump out is slow, we can create increase of the accumulation of calcium, and the higher the frequency, the more it resembles a response to just step of light. And that's basically how we simulate the continuous lighting conditions by operating at these high frequencies, which leads to flicker fusion. The other mechanism that helps with flicker fusion is a filtering of glutamate release in a synapse between bipolar and ganglion cells. If you look at the this transient response with a much lower sustained rate, it becomes very similar to just response to a step of light at frequencies above flicker fusion, above 30 hertz or so. Okay, now what are the pixel densities that are required for restoration of reading ability? For example, normal vision corresponds to sampling of 5 micron per pixel. 30 cycle per degree corresponds to this size. The legal blindness level 2200 acuity is 10 times larger, so corresponds to pixels of about 50 microns. So keep these numbers in mind. We'll discuss different pixel sizes as we go. Our system is completely wireless. It operates by light. So it includes augmented reality glasses that have a camera, an image processor that delivers these images to video goggles, where projector projects these images onto the retina, onto the implant, using invisible beam, near infrared 880 nanometers. So the reason we use invisible beam is to avoid any perception by remaining photoreceptors. And we have to intensify this light compared to ambient and have it pulsed, because otherwise it will be insufficient for stimulation of neurons. So because it's intense, we want to make it invisible, and because it's pulsed also, it's good to have it invisible. So the implant converts light into current in each pixel and stimulate nearby neurons, while peripheral retina nearby remains unaffected. So when light is on, current flows in one direction, we polarize the cells. When light is off, it flows back because interface capacitive. And as I said, we rely on transmission through the retinal network to ganglion cells and then to the brain. So two functions of photoreceptors that I mentioned. One is conversion of light into change in cell potential, and the other is release of this information as a rate encoded into a rate of release of glutamate on second-order neurons, is replicated in our case by photodiodes doing pretty much the same. They convert light into electric current that generates electric potential in a medium, and we directly polarize neurons and affect their cell potential by just having it in proximity to the electrode. So the electric field in front of the pixels is basically works as a synapse that regulates the cell potential of second-order neurons. Other functions like adaptation is performed by camera autofocusing. We can do zoom, image, and contrast enhancement, and so on. Because the camera is outside, it's very convenient for us to play with it outside the body. So instead of natural three-layered structure of the retina, we have three-layered semi-natural structure where one layer is replaced and two others we hope are preserved to the extent possible, and we rely on this preservation for signal encoding. This is my longest project. We started with this idea in 2004. We got to clinical trials in 2017, and I'll show you the results today. Now, the surgery, because the implant is wireless, the surgery is quite simple. We inject fluid in subretinal space, then make a retinotomy equal in size to one module of this implants, and then we deliver by injector these modules. We can do more than one. In clinical trials currently there is only one module, but in animals we did up to 7. You put them, tile them in subretinal space, and then retina is reattached using perfluorocarbon initially, and then everything else is wireless. So the image is captured by the camera, processed and delivered to the eye as pulsed near-infrared light, invisible to photoreceptors, but visible to silicon chip. And each pulse of current of light is converted to pulse of current by the photodiode. So the implant itself is very simple in a sense. It's just a converter. All the sophistication of encoding or improvement of an image is done outside the body. These are the implants we are making at Stanford. The human version is done in a different fab, but this is how our chips look like. So there is an active electrode in the center, return in the periphery of each pixel. There could be 1 or 2 diodes in series that control the voltage. And sizes that I will be discussing today go from 100 microns all the way down to 20 microns in our latest generation. So why silicon and why the dimensions that we have chosen? We want to make this light invisible, as I mentioned. So peak of retinal sensitivity in humans is around green light, shown here with blue line. And we want to make it as less visible as possible. So at 880 nanometers, it's about 10 million times below the peak sensitivity. If you go another, maybe 10, 15 nanometers, you can get 10 to minus 8. So that's sufficiently invisible. But going further into the infrared is actually difficult because water absorption kicks in and light is not, just will not reach the retina. So we are limited to this range of 880, maybe 950 nanometers. Fortunately, at this wavelengths, this wavelength corresponds to peak of responsivity of silicon. So quantum efficiency is very close to 1, and conversion is about 0.6 ampere per watt at its peak. And so silicon is the best material for this wavelengths. And the thickness of our implant or penetration is defined by penetration depth of light, which is about 25 microns. And we want to make this implant as thin as possible, so it will be as light as possible, and we don't need to, worry about its movement. It will be because it's held by retinal attachment forces only. So our thickness is actually 30 microns, just above that penetration depth, and we have double path. The light goes down, is reflected from the metal on the back, comes up, and so we absorb more than 90% of light this way. And that's why the dimensions of our implants are 30 microns in thickness, and it's crystalline silicon. So it's important to encapsulate the implants. It turns out that the body is very aggressive medium. It dissolves pretty much anything, including silicon and silicon oxide. So we develop protective coating to avoid this sort of erosion. The coating called silicon carbide, it's transparent, it kind of looks reddish, and that protects the implants very well. So currently, after already 5 years, even in humans, we see no erosion, and implants look pristine. So they will certainly live longer than patients. Okay, so let's talk about the signal preservation or encoding preservation. We started by studying the retinal response ex vivo using multi-electrode array. So retina is placed on multi-electrode array, and we can read out the signals from ganglion cells. We can project normal visible light and get response of the normal retinal response, or we can project near-infrared light, place this array on top, and study prosthetic vision in normal retina or in degenerate retina. So we see a lot of features of normal vision preserved, fortunately. So normally, one of the features, for example, is antagonistic center surround. You can see here the structure of receptive field of on and off ganglion cells with antagonistic surround, and that's normal retina. If you apply electrical stimulation to this normal retina, healthy retina, we see a reversal. On cells become off cells become on. And this is because, as I mentioned, our implant polarizes cells, while light depolarizes, hyperpolarizes photoreceptors, while our polarization depolarizes them. So it's basically like a dark stimulus, but everything else is preserved. But that's not very interesting. What is more interesting is the degenerate retina, where there are no photoreceptors, and yet we see antagonistic center surround. And that is because amacrine cells still do their job of lateral inhibition. And as you can see, the depth of modulation of antagonistic surround actually is similar to normal. Now we see on responses and off responses and combinations of on and off. We think that the on is actually excitatory responses are in on ganglion cells, and we judge it by low background noise, which is characteristic to on pathway. We see off responses or inhibitory responses in cells with a high background noise, which are off cells, especially in the degenerate retina, and we see some combinations. If you study contrast sensitivity by applying steps of light, we see that compared to normal vision, contrast sensitivity is decreased by about a factor of 6 or so. And that we think maybe in part because there are no horizontal cells, they're basically disconnected. There are no terminals of photoreceptors, and they do a lot of this contrast enhancement. But we can compensate for that by contrast enhancement of an image before we project onto the implant. So in summary, the reservation of retinal signal, the features of retinal signal processing, we see on and off responses, so it's quite rich, not just excitatory. We see antagonistic center surround, we see flicker fusion, and that's very important because we want to induce steady percept, and yet we have to use pulse light, so we operate at high frequencies. We see nonlinear summation of subunits of bipolar cells to ganglion cells, and this is another very important feature for high resolution. The receptive field of ganglion cells in rats is about 200 microns or so, and yet we see that resolution, I'll show you acuity results, is with alternating grating in rats is about 28 micrometer. How they do it? They have nonlinear contributions in the synapses between bipolar and ganglion cells and nonlinear rectifying, and therefore the retina is sensitive to subunit, to contribution from each bipolar cell. And the response is decoded from population response. This feature is preserved in prosthetic vision, and that's very important for high resolution. Contrast sensitivity, as I mentioned, is reduced, and therefore we use contrast enhancement between the camera and the projector. Okay, now moving to animals, we study the responses of visual cortex stimulation in rats. We implant this arrays in subretinal space in rats. You can see this implant is 75 microns. On OCT, the side view where the top surface of an implant is visible in white. And you can see that it's very close to the nuclear layer, our target layer. And the implant is held just by retinal reattachment, which is driven by mostly by pumping of RPE, pump out of water. And this forces are sufficient to hold the implant steadily inside. And that's very fortunate. That's because the implant is so thin and light that it doesn't create this problem of movement. We study the response by recording signals in visual cortex, and we can here compare normal vision in rats with normal, retina, and prosthetic vision by applying either green light or near-infrared light with or without implant. So these are how the signals look like. They're quite similar. Prosthetic signal, prosthetic VP arrives earlier because we skip phototransduction. So how do we measure visual acuity? Besides teaching our rats to read, we also use alternating gratings. And so we can apply alternating grating at different bar widths, and the amplitude of this response will decrease with the decreasing bar widths until they stop resolving the change in image, and that's a limit of acuity. So natural acuity in rats is about 28 micrometers. And when we compare it to prosthetic acuity with different pixel sizes, we measure it with 75, 55 microns, and now actually lower even, but here before clinical studies, this was the result. We saw that they match pixel pitch. So that was very exciting, meaning that as much information as we could deliver with these pixel sizes, brain was responding to. So with that, we moved to a clinical implementation with Pixium Vision. As I mentioned, they manufactured the human version of this pixels shown here. It was an array 2 by 2 millimeters in size with 100 micrometer pixels. So we started quite conservatively with 100 microns. And the size, the thickness was exactly the same as we used in red, 30 microns. Same materials, iridium oxide with silicon carbide coating. So this projector on augmented reality glasses is DMD projector. So it means that intensity of light is on the projector is the same on the array. We control the stimulus by duration. And for normal vision, you cannot distinguish between modulation by duration or by amplitude. There are projectors of both types. And the same goes for prosthetic vision. So that's a DMD projector. We can operate at different frequency ranges, up to 60 hertz actually. Normally, our current rate is 30. The visual field projected instantaneously visible is shown here as an ellipse of 18 degrees. It's pretty much the same as Google Glass. If anybody tried Google Glass, that's pretty much the field that you have. So within this field, the patient can freely move his eye or her eye, and outside this field, he has to move the camera or the head, basically. The OCT shows very good opposition of INL in front of the implant and stable positioning. So we started with first a trial called feasibility trial with 5 patients, all in France, all done by same surgeon, Yannick Lemaire. And all 5 patients reported bright white-yellow patterns of perception of in retinotopically correct locations and shapes. Oh, I forgot to mention that before we transitioned from rats to humans, actually the Pixium initiated together with Institute of Vision in France additional studies, first of feasibility of surgery in pigs, and then study in non-human primates of validating that the stimulation thresholds are as expected using saccadic movement, and that was done successfully before translating into humans. Okay, so going back to humans, all 5 patients perceive bright white-yellow patterns. They describe it as kind of sun color, not exactly white, but sun color, whitish. And we started with virtual reality glasses that just to make sure they see nothing but electronic vision. So we block all the normal sight, and so the first tests were done with opaque glasses. So you can see here the first study.
Ah voilà. Alors, là, je suis sur le R.
Ouais.
Le R.
Là, c'est la deuxième lettre.
Alors là, je suis sur le O.
Oui. La
La
troisième.
troisième, le U.
Et la quatrième.
Et la quatrième.
So that's first generation. Then, after completion of the study, and the results were very encouraging, they saw pretty much down to single pixel resolution. We moved to a next phase of the transparent glasses that I described earlier, but here you can see that a clinical version of that on a model. By the way, these are not patients. Both of them are just showing the glasses. So here the patient can have normal perception in unoperated eye, and peripheral vision in operated eye is not obstructed. So to make sure that we know what they read with prosthetic vision and what is normal, we do several tricks. First of all, we can invert contrast. For example, instead of white on black, we show black on white, we show white on black. And we ask about color of perception. We can play with zoom, which will only affect electronic version and so on. So here is the test now with the TDRS chart of a patient still from the first cohort, but with these transparent glasses. You can see on the right what camera captures and what we project.
Oui. Oui.
Oui.
Parfait.
5 sur 5.
So this was a patient from the first 5 cohort, and reading a TDRS chart. Now we wanted to see if they can perceive simultaneously prosthetic and normal vision.
Et l'autre doit être diagonale gauche-droite.
So for that, we project here a line that is visible easily to peripheral vision in green, and then in the center we projected that prosthetic pattern on display and asked relative orientation. As I have no problem seeing them simultaneously. In fact, if you say orient them same way and ask about continuity of perception, the patient described it as a green line that begins in upper right corner, for example, going down, becoming white, and then becoming green again. And they can tell relative widths and so on. So it's really simultaneous perception, which is very exciting. because it tells you that normal code perceived by the brain from the periphery simultaneously with abnormal code, prosthetic vision in the center, and yet the prosthetic code is close enough that it is perceived as form vision and simultaneously with normal. Okay, so the summary of that first 5 patients was that subretinal implantation is feasible and safe. The peripheral vision was not affected. The natural acuity did not decrease. Now we have almost 5 years follow-up, and the implants are stable, and peripheral vision, as I mentioned, was not affected. The resolution was very close to the single pixel size limit. Single pixel measured in a gap of Landau C, for example, of 100 microns correspond to 20/420 acuity, and we got the range down to 20/438. So pretty close and very consistent. Average was only 17% below that limit. And as I mentioned, the central prosthetic vision, natural peripheral vision are perceived simultaneously. So with that, the company, Pixium Vision, moved to a bigger trial, second phase pivotal trial with 38 patients, now in all over Europe, not just in France. And before I describe it, I'll mention one other feature. I mentioned that the glasses augmented reality glasses have an option of zoom, and we tried that, allowing patients basically to set their preferred zoom settings for the most convenient reading. So they could choose between 1, 2, 4, and 8, and all of them were selecting whatever they like for reading small text, most convenient settings, and all of them exceeded 2100 acuity, some as high as 2063, which corresponded to 8x settings. Obviously, zoom decreases visual field, so it's a trade-off of scanning versus simultaneous perception, but that was at the patient's kind of preference. So with that, we moved to that bigger trial, 38 patients, called Primavera trial, and I will tell you about preliminary results. Official results are not released yet. It will be hopefully soon, but the follow-up measurement period ended in February, so the preliminary results are coming. So out of 38 patients with geographic atrophy that participate in this trial, the primary endpoint now was 2 lines of visual acuity improvement measured by ETDRS chart. So it's not anymore just sensitivity or Landau C, it's real letters and real chart, just standard ETDRS chart. For trial success, based on the statistics, the definition of success was more than 71% of patients need to pass this primary endpoint. And the results, so 12 months follow-up was completed at the end of 2023, and last measurement, I think, was actually in February 24 even. The endpoint was performed in 33 out of 38 patients. 5 patients did not complete follow-up. Actually, 3 died, 1 health issue, 1 silicone oil not removed. These are elderly patients. So out of this tested patients, 79% passed the primary endpoint. And the average improvement was not 2 lines, but 5 lines of visual acuity improvement. Now, objective measurement of no magnification. So with zoom, obviously it depends on the patient's skills, how stable they are, how they like, using zoom. But just with no magnification, if you present a letter and measure acuity 1:1, the measurements were showing that with all the tested 33 patients, acuity was 20/458. So it was about 10% below sampling limit, or above, should be worse than sampling. And with patients who passed this 79% that visual acuity point, the acuity was exactly at 1 pixel limit, 20/420. So that's very exciting. So it's very consistent. It's not just one-off. So let me show you some videos of how patients perform, some of them. So this is a patient reading from the page of a book. You will see both how it looks on a page, and you will also see how it looks, what camera captures and what we project from the camera to the eye. So here, as you see it the page itself, but the camera will move to a computer to show what is captured. So now she lost the line. She's looking. So that's the patient reading from the page. And you can see that the projected image corresponded to approximately 5 letters per implant, which basically corresponds to a really sampling limit of about 5 pixel by 5 pixel per letter. Here is another video demonstrating patients writing, playing crossword, and you can see how he sees it and how, oops, sorry. Oops, what happened? Okay.
Il n'y a qu'un seul L, ouais. Et 2 M.
So here, patient needs to fill the crossword puzzle. You can see what camera captures on the left, what is projected on the right.
Système de point de référence. Ouais.
And so on. So patients can basically see that in real time. You can see how fast is that feedback between vision, and that prosthetic vision is pretty much nearly as fast as normal. So you can perform these writing tests on a page. Now, for other more practical kind of tests, patients were taken to different locations to find signs, to read signs. Like this patient, for example, is in a subway. Needs to find directions, read the signs, find the errors, and so here is a video. You can see that he can read and find the error, and then he can also read the names of stations and find where he needs to get out. Here is maybe, let's see if some reason the sound is low here. So, and here is another exercise where patient needs to read and then write missing numbers. You can see what camera captures, how she sees. You can see what camera is projecting kind of into the eye, and that's what she is looking at. Okay, so one of the questions was why the patients see so well, and why there is no confusion between on and off pathways that we were concerned about. My colleague and friend E.J. Chichelnitsky, who is working at Stanford now, always was telling me that it won't work because you don't respect on and off, difference between off channels. You stimulate them simultaneously, and the patients will see patches of black and white, and that's not the case. Patients report bright pattern on dark background if that's what we project, and no confusion. And oh, I forgot to mention one other thing, the perception of steady image with pulsed light. So we tested this flicker fusion side of the story by projecting different frequencies, and patients clearly see pulsed light when the frequency is low. And then at around 30 hertz, it appears pretty steady, and they like even more if it's projected at 60 hertz. But currently, the system is set up for optimal 30 hertz, so that's what we use in clinical testing, and it appears quite steady. So this idea of flicker fusion really worked well. Now, so why there is no confusion between on and off pathways? We don't know the number for sure, but here are some hypotheses. So first of all, for odd pathways, there is only on. They naturally split into on and off after bipolar cell, so there will be no confusion. And that's fine. For on-con pathway, also everything is fine. Stimulation of on is excitatory, should be perceived like that, like natural. But for off-con pathway, stimulation of con bipolar cell should result in off-percept, dark percept maybe. We don't know exactly, but that's a concern, and yet it isn't happening. So why is that? So it could be several reasons. One, that in degenerate retina, off ganglion cells increase their spontaneous firing rate, and that requires a lot of spikes to be elicited to be noticed. So basically, your signal to noise is diminished, and that may be why this pathway is attenuated. The other could be that on and off bipolar cells, different lengths. On bipolar cells have longer axons, and therefore their threshold may be lower. Also, on bipolar cells may be depolarized due to absence of glutamate input as opposed to off. And so they basically reduce the on pathway have higher sensitivity than off. And another possibility is it turns out that retina has asymmetric inhibitory pathways in mammalian retina. The on pathway have inhibitory input on off, but not other way around. And this is mediated by amacrine cells, A2, that allows on bipolar cells to hyperpolarize off bipolar cells and thereby diminish their input. And it is not happening in opposite direction. And that's maybe due to adaptation of the retina to natural scenes that have more contrast levels below the mean than above. And that asymmetry is translated to this asymmetric structure of the circuit, which may work to our advantage in rectifying this asymmetry, this non-discriminate stimulation, providing predominant on output. So these are kind of some thoughts. I am curious to hear yours if you have some other ideas, but let's talk about the future. So now that it works so well with 100 micron pixels, how far we can push it? What can be, how low, how small the pixels can be? And the problem, it turns out, is very fundamental, and it is common to many applications where you want to, if you want to try to reduce pixel size and you have active electron in the center, return and periphery, the electric field as a little fountain is confined to this pixel size. And then you shrink the pixel, you shrink the penetration of the field into the tissue, you just cannot reach the cells you need to stimulate. You can compensate a little bit by increasing light intensity and current density, but there is a limit of safety and it's not too far. So it's not really scalable by far. So we estimated this by modeling the system, and I'll skip the details. If you're interested, I will discuss a model, which is beautiful, separately, but I can tell that we can convert projected light intensity using this model into voltage drop across the cells. and predict what is a voltage threshold. And then for any other configuration of the chip, we can tell what will be the light threshold that will be required, light intensity threshold. And we already see that just going from 100 micron prima pixels to 75 will require increase in light intensity from what we use now, about 3 milliwatt per unit square, to 8, which is close to safety limit. So we cannot really go far with that. So to overcome this geometrical limitation, we need to change geometry. And we change it to 3-dimensional geometry by adding pillars that improve proximity to target neurons, or honeycombs that allow cells to migrate in and become exposed to very strong field inside the honeycombs, or by what is called current steering, allowing neighboring pixel to collect current instead of the return at the pixel edge. And that increases penetration depth by about a factor of 3 or so into the retina. So we tried all of these approaches, and we also improved the structure of a pixel by vertical junction. I'll skip that engineering aspect unless you want me to discuss it during Q&A. So we reduce the pixel size with all the streaks to 20 microns. So here you see 55, 40, 30, and 20. And we measured again acuity in rats using alternating gratings. You can see here. The response to alternating gratings we measured with visible light and with prosthetic stimulation to again compare apples to apples. And you see that with 40 micron pixels, the signal drops to noise level at exactly the pixel pitch size, which is it's hexagonal array, so it's a pixel size times cosine of 30 degrees at 34 microns. And with 20 micron pixels, we were expecting about 17 micrometer, but we got only 28. And the reason is that we now actually matched biological limitation. Rats don't see better than 28 microns. So now our pixels are too small for rats. They don't see, their wiring is doesn't allow this. So our pixels are now too small for rats. But for humans, these pixels are still larger than natural limit. So 20 micron pixels correspond to acuity of about 2080 in human patients without zoom, just 1-to-1. And that's our next goal. So I mentioned that we rely on network-mediated conductivity, but we never really directly proved that. So recently we did this experiment by applying blockers and preventing transmission of signal from bipolar to ganglion cells. What will be the consequences of that if you directly stimulate ganglion cells and skip the network-mediated encoding? What will be the consequences of that on vision? So we applied this cocktail of blockers, blocked the signals, and we see that indeed, if you increase the stimulus strength, you can overcome blockers and elicit response directly in ganglion cells with different pixel designs. It's slightly different ratio, but you can do it. You can induce direct stimulation with our pixels by bright enough light. But if you measure a visual acuity, it's completely gone. So without blockers, you see blue signals, very strong, nice response to alternating grating. As soon as you applied blockers, yes, you can elicit some response in ganglion cells, which probably is perceived as light, if it would be patients, but there is no form vision. The acuity is completely gone. And that's remarkable. It means that really what we were thinking about, the need for network-mediated encoding for high-resolution vision is indeed the case. You can get light sensitivity, but no high-resolution vision if you skip the network-mediated stimulation, go directly to ganglion cells, at least with our implant design. So in a model, we see that there is a nice encoding of the signal in polar cells, but pretty much random response in ganglion cells, and it doesn't encode form vision. Same goes with a monopolar pixel design. Again, you can elicit a lot of light response on RGCs. It doesn't carry visual information because of the resolution of large receptive fields of ganglion cells doesn't allow. So with that, we now are optimizing our pixels to translate this advance from rats to humans. And in human retina, it's thicker, and there is a debris layer between the implant and the inner nuclear layers that is absent in rats. So we are now optimizing this implant for human retina with the criteria being maximum stimulus strength, maximum contrast, but still as good selectivity between bipolar and ganglion cells as we have now with current implant Prima 100. So we optimize electrode geometry, some electronics inside the chips, and return electrode geometry and software of image projection sequence to benefit from all these features. Another interesting feature, it turns out that you can actually upgrade an implant. Because the implant is not really attached, just sitting in subretinal space, turns out that you can actually remove it and replace with a high resolution implant in the same location. You can see how the implant is removed several months after implantation in rats, where it was measured and functional and so on. The old implant with low resolution is removed. The new implant that you can see here with 20 micron pixels is inserted. It is slid in subretinal space in exactly same location as you can see in these fundus images we judge by the blood vessels location. And implant again is reattached. You can see INL right above it. And when we measure stimulation thresholds, they are very similar to pristine retina. And grating acuity with new implant now matches the 28 micrometer limit. So it's really exciting that you can slide out the implant, put a new one, and it works up to the resolution limit of the rat's retina. So with that, I want to thank our team and our funding, our collaborators in Paris and in UK and our funding. And thank you for your past contributors. We have a long list. And thank you for your attention.
Daniel, let me thank you first of all for your presentation today, and we will go to Zoom to Thomas very soon. I will just ask you a very quick question related to remaining structure of the retina after the implantation. You introduce a barrier between RP and the rest of the remaining retina. Do you see, and again, do you see this over time, any changes in that part?
Yeah, so the implant separates retina from the choroid, and if you place it in a normal retina, in healthy retina, it actually will kill photoreceptors because they rely on the nutrients and oxygen coming from the choroid. And that actually is very convenient model of AMD, that you basically introduce an implant, it creates a scotoma and prosthetic vision right there, and everything else is normal. And we actually use this model. And Richard Kramer in Berkeley actually also inherited this model from us, and it's very convenient. Now, for inner retina, we don't see any negative consequences of that because it is fed from the inner retinal vasculature. So inner retina survives, at least in rodents and humans, pigs, and so on. It's not so in rabbits, by the way, because rabbit retina is avascular, and it dies if you separate it from the choroid. But human retina has inner retinal vasculature, and it survives. And we don't see, any like strong gliotic or fibrotic seal forming unless you injure the retina. If you injure, and there were several patients where the implant was pushed into the choroid, there was bleeding, and then you see formation in some of them of fibrotic seal. But if the surgery was atraumatic, then retina is very quiet, and you have seen the OCTs.
All right, let's move to Thomas. To Thomas, and then we'll go to Maciej.
Yes, thank you for the great talk. I have a question about the flicker fusion frequency that you mentioned. If I remember correctly, the second site implant and the Tübingen implant, they had the problem if their stimulation frequency was too high.
Yeah, it was fading.
Then the perception was fading.
Yeah.
And you said it's good for the patient to have high frequency. So why is that?
Yeah, that's very good question. It's indeed very interesting that we heard the complaints about fading from several groups working on prosthesis. In our case, it's not the case. So one issue that may be different, there may be several, but one of them is if you fix an implant on the retina, like second site, and deliver a static image it will fade away even with our implant. It's adaptation. We see it also ex vivo. If you provide the same stimulus over and over again at high frequencies, the response will go away. It's adaptation. And that will happen if you fix your eye and won't let it move, right, and look at the same picture, let's say, or it will fade away. But eye movements correct that and refresh an image when you look at static image, and therefore it prevents fading. So our implant is light sensitive and it's constantly moving with eyes. And I think that's very important. If you would take this away, this would fade. The implant static image would fade. You can fake it by providing correction of shifting an image based on eye tracking, for example, but that's, it's a separate story. We don't need it. But if you don't do it, if your image is static and it is sitting on the same location on the retina, yes, the response will fade away, especially at high frequencies. There may be other reasons for that, but at least this is one.
All right, Maciej. Thomas, do you have a second question?
Yeah, it's more of a subjective question. So when I saw this crossword video of your patient, that looked like really hard work. Do they enjoy using their prosthetic vision?
Well, I don't know if all of them enjoy doing these tasks, but all of them are allowed to take it home and do whatever they please. Some are more, active users, some are less. This lady that you have seen writing numbers and so on, she enjoys it. She actually plays cards, and I've seen a lot of videos of her. And, it depends on the personality. Yeah, I was surprised to see how high zoom they liked. I thought it will be difficult to have high zoom because you need to stabilize and your field is small, but they seem to actually like it because they can read small font and even directly from a page. So that was actually surprising to me. But in terms of overall statistics of how many of them enjoy doing what, I don't know. Hopefully, when company will announce the official, clinical results of this trial, they will have something about quality of life kind of questions.
Okay, Maciej.
Okay, thank you, Daniel, for the beautiful talk, and these are really magnificent results. I was wondering, I have very technical question about, the optimizing the pixel size. So when you go down with the pixel size and you are changing the geometry, are you also affecting the capacity of these electrodes and the response times, or is more or less the same?
So capacity of the electrode is defined by capacitance per unit area times the electrode area, right? And we keep the same material, iridium oxide, CyROF, and so that doesn't change. The electrode size, yes, it is optimized, but it is not changing if it's elevated on a pillar or it's at the bottom of the well, it's the same. What is really changing is the field shape. For example, in a well, the field is almost vertical, which is very advantageous for the cells that are oriented vertically. So you create you don't waste your field on a sideways, so to say. You go across the cell and polarize it to the maximum. So these are the geometric considerations, really, that field shaping. And by the way, this is one of the most I would say the most fundamental limits in nature are geometrical. That's where all the origins of laws of physics come from geometrical considerations of symmetries and so on. And so if you have a geometrical problem, it is very fundamental. You best serve by changing geometry to try to address it if possible. And this is one of the limits, for example, in cochlear implants. Cochlear implants until now didn't improve resolution beyond, say, 12, maybe 20 electrodes for exactly this reason. The distance between electrode and target neuron is about 1 millimeter, just because of the anatomy of the cochlea, and making spacing smaller doesn't help. And so that's really, if you can solve geometrical problem by changing geometry, then it's a path forward. If you can increase, by brute force a little bit, as I mentioned, but not really fundamentally. So by changing the field shape, this is where you get the biggest bang on the buck.
Okay, thank you.
Okay, Ben.
Yeah, it's my turn. Yeah, good talk. So basically, I'm just curious about the mission. You show the patients if they can see, and what do you have the control showing how well they can see before your implant?
Yeah, so we have videos I didn't show of comparison. Yes, these patients have vision, so it's not correct to say they don't see. They see, but low resolution with peripheral vision, PRL. They can, walk, for example. They don't bump into tables and so on, but they cannot read, or at least, the acuity is limited. So the control we allow patients to read with just their normal, glasses, whatever font they can, and then decrease the font size below what they can read, and then allow to use our system for comparison. But it's the study that outcome that of the Primavera was exactly this measure: how many lines of visual acuity improvement they can get in a operated eye. I think the control eye sees better, so that's a separate question. But I think in a treated eye, so it's not zero starting point. They have some acuity, and then you can improve by providing the system.
Roy, are you there?
Yes, that was a wonderful talk, and it was a learning moment for me where things have progressed. My question is that can these implants be engineered to elute drugs?
Maybe. Yeah.
And the reason I asked this question is you mentioned that if the surgeon finds that there is an injury, then there could be complications.
Yeah.
But does the implant itself drive any fibrosis on the edges?
Yeah, so as I mentioned, in normal atraumatic surgery, we don't see signs of fibrosis above the implant. But I think there is fibrosis underneath because it's a spherical surface. You put something flat, there will be some gap of, depending on the implant size, of between few microns in rats to maybe a few tenths of microns in humans. That probably will be filled with something of fibrotic nature, I presume. And if you would remove an implant, we actually, when we see histologically in rats, when now we started removing implants and replacing them, you see some kind of fibrotic-like tissue on the back side of the implant, between the implant and missing RPE. But if there is an injury, then we see much stronger fibrotic response. You can control it by injection of anti-VEGF, and we actually had patients that had bleeding, and then you can control that with anti-VEGF injection, exactly like with normal, AMD.
All right, we will go back to Thomas for the last question from the Zoom, and then we move to 5 questions from the room. Thomas, all yours.
Yeah, what I wanted to ask is, you have this camera image feed that you have access to all the time. And that made me think that one could support these patients even more by AI features like text-to-speech, object recognition, that you can whisper in their ear what the AI tells them. Are there any plans to take advantage of that?
Well, yes. First of all, the simple answer, you don't need an implant for that. There is a product called OrCam, which is a camera that you can clip on glasses, and it is connected to a smartphone and has all these features of image recognition, and it can read in voice, some text and stuff like that. So yes, you don't need an implant for that. You can benefit, but patients want vision. If you ask them, it's vision substitution, it's a different avenue. Yes, you can provide something like that. It's not vision, it's substitution. They want vision. So the features that would benefit but still remain visual is something like image simplification, which would benefit from AI indeed. So if you look at the bill, it may simplify, for example, the image to show numbers and not all the details of the $1 bill with all the complex drawings. Yes, that probably can be done. It's not yet implemented, but that's something that could be done for simplification. But my interest currently is to, first of all, improve the performance of electrode-electrolyte interface, or the implant retina interface, to the best of its ability, to see where is that limit and see if we can implement that resolution first. And then you can add on top all these nice features of contrast enhancement, simplification, and whatnot.
Okay, let's just move to a room. Priya?
A very impressive talk, Dr. Palanker. I have a couple of questions. Number one, I would like to know whether your study group, the human study group, included patients affected with both wet and dry AMD. Second one, when does a patient need an upgrade? Is it when the disease progresses or when the implant is old enough? Thank you.
Well, so first of all, currently the patients are dry atrophic AMD, geographic atrophy. But some patients progress to that stage directly from dry AMD, and some progress after a wet phase. And that's, I think, both options are now available. I think in a feasibility study, it was a selection of only patients without history of wet AMD, but currently I think it's open to all of them who progress to atrophic phase. Now, replacement is currently hypothetical. We do it in rats. We didn't do it in humans. I'm not sure physicians will be happy to operate against the elderly patients and replace an implant, but it's an option. And if it works well, we'll have a real kind of market for that and so on, then it will be done as soon as the new generation of an implant is available. You don't have to wait longer. If you can replace it with much higher resolution implant, why not? But currently, what I've shown was done only in rats with this upgrade.
Okay, Aru.
Hello, thank you for the great talk. I have one question about the clinical trial. What was the rationale behind choosing GA patients over retinitis pigmentosa patients for this clinical trial?
Yeah, several of them. One of them, I think Brian Jones will like this reasoning. We are concerned, and Brian told us many times, that in retinitis pigmentosa patients, especially when there is a end phase of the photoreceptors are lost, the retina is undergoing very aggressive rewiring. And the most aggressive when all of the photoreceptors are gone. And so when the field is decreasing, and it takes many years, and the last photoreceptors in the center are lost and retina badly rewired, we were concerned that introducing an implant into the center will basically not restore as high visual acuity as we hope to get in AMD patients, where retina doesn't degenerate next to the implant. Right outside the implant, it's pretty much normal, and therefore the central few millimeters are better preserved. So that's kind of one reason. And the other reason was just quantitative. So the number of AMD patients is much larger than RP. And if you want to have a company, a sustainable business, you need big market. So that's another reason. But in principle, we can move to RP, but I would start with Stargardt vision because it's very similar to AMD, that central vision is lost and peripheral is preserved, for at least a long time. And that would be the first step in direction of RP to test it.
John.
Hello, thank you for this great talk. 5 lines of vision improvement is pretty amazing. I was just wondering, you're placing these implants at the foveal region. At the fovea, there's like a depression or thinning of the internuclear layer and the ganglion cell layer, which is what's trying to be stimulated. So how does that account for the lack? Yeah.
You're talking about foveola. It's a very central, maybe 300 microns where there is a missing INL. As I said, we don't care about ganglion cells spreading further because we don't stimulate them directly. But yes, there is probably a small kind of blind spot due to missing INL in the very center of the fovea, and this 300 microns may not be, restored. But if this is all you have is a 300 micrometer little scotoma, it will not be perceivable. If you can compensate by scanning and everything else is working, I don't think you will notice this small spot of missing information. But yeah, I presume that in this little area, there is nothing to stimulate.
Okay, Professor Vice Chairman.
Hey, Daniel, this is Vladimir. Very exciting work. Thank you for sharing. And I was wondering about the off bipolar cells, so thank you for addressing this. My question is about spontaneous retinal waves. So at least in rodents, when the outer retina starts to degenerate, the retina develops those spontaneous waves reminiscent of what happens early in development. So first, I don't know if that occurs in humans in the foveal region, but are you concerned that this, first of all, do you know what happens with those waves after you introduce the implant? And are you concerned that that might actually interfere with the signal processing from your implants as well?
Yeah, so retinal degeneration and retinal rewiring as a part of it affects firing. I was showing the increased spontaneous firing rate in ganglion cells in one of the slides. Yes, certainly it's a consequence of degeneration. Actually, Richard Kramer in Berkeley studies that in quite great detail, and we collaborated on that. So yes, we know that retinal degeneration has consequences, and the firing rate is abnormal. But it turns out that on top of that, you still can introduce prosthetic vision, and patients see patterns. It's not just light, it is form vision, it's immediate, it's fast. And that is, I think, is the first time actually that we see with this implant, unlike all other attempts to restore sight, we see really form vision, not just light sensitivity where you can scan and figure out that you're looking at some bar and it takes time and so on. Here it's instantaneous form vision. And yes, it probably comes on top of some abnormal retinal firing, and maybe some of the features of signal processing are not preserved. But the key question here in medicine in general, it's good enough or not. So for cochlear implant, for example, what was good enough for reimbursement was ability to recognize speech. I think here for these patients, what is good enough will be judged by ability to restore reading and face recognition. And it may not be at the level of normal vision in terms of dynamic range, contrast sensitivity, and so on, but with all the help with the camera and so on, it may be, and I hope, is good enough for the function. But yes, it may not be as good as normal because of the spontaneous noise increase and so on.
Just a quick follow-up. Did you actually check if the firing rate returns to normal after you introduce the implant?
Oh, no, we didn't check that because firing rate, we can only check ex vivo, and I showed the ex vivo measurements of, implant stimulating degenerate red retina, but so it's not, we cannot tell what happens, after that over time if retina kind of. What we can tell is what we actually looked at is density of synaptic connections in a plexiform layer. So it's connections between bipolar and ganglion cells. And we thought that upon chronic use, it may be kind of returning to normal or becoming at least more dense. And we didn't see it. We stimulated rats for several months, chronically every day. And we didn't see significant changes in density of in a plexiform layer compared to like control areas outside the implant.
Thank you.
Francis?
Thank you for the talk, Dr. Palanker. So you highlighted how your system registers images in real time comparable to natural vision. I was curious if the newer designs of the three-dimensional electrodes that you were looking at had an effect on this real-time imaging speed.
Why would it have an effect? The electric field spreads with the speed of light, so it's pretty much instantaneous in femtoseconds when you turn it on. Or capacitive, current will limit it to maybe a sub-microsecond. I don't see a relationship between field geometry and the perceptual speed or rate. You stimulate neurons, they respond in milliseconds or tens of milliseconds later, and VEP is maybe 100 milliseconds later. So it's all much slower processes than creating the electric field in a pixel.
Okay, we had a great conversation. Our last three questions. Philip.
Hi, Dr. Palanker. It's Philip Kaiser. Really nice work. So, is it on? No?
Oh.
I can hear you. I cannot see you, but I can hear you.
Okay, maybe it's better now.
Yeah.
Really nice work. I have two quick questions that are related to some of the things that have already been asked. So you've been focused on
GA where the RPE is gone for the most part, and you're putting the chip on top of that. So if you were to move to something like retinitis pigmentosa where the RPE is still present, would that change the approach given how active they are in terms of pumping ions and water and so on? And if you put the chip on top of the RPE, do they degenerate?
So I can tell you what we see in rats. In rats, we use the RCS rats, which have RPE still. It's kind of dysfunctional. That's why the photoreceptors are lost. They don't phagocytize outer segments, but RPE is there. And so when we place an implant, it's exactly the situation that you describe, like in RP patients, and it's working. So all the results with rats that I was showing you in terms of acuity is measured in this model. And even I can tell you even more. We use also normal rats. When, as I mentioned, if you place an implant, it will kill photoreceptors above it. It's basically a model of AMD. It has normal RPE everywhere, including you start with normal RPE under the implant. I don't know if it stays normal after that, and it's working. So I don't think placing an implant above RPE and separating it from the retina has much of an effect on inner retinal cells. Obviously, it has very strong effect on photoreceptors if they're there. It will kill them because they need the feed from choroid. But inner retina is fed from the inner retinal vasculature, and so we see that it's surviving fine.
Hello, Dr. Palanker. That was really interesting. And my question is a little bit maybe from the science fiction side, but did you think maybe, or is it planned to have those cameras implanted in the cornea, for example, together with the cornea transplant, or, anything?
No, I don't see a point of doing it. I told you that there is a big benefit of having complex electronics outside the body on the glasses where you can take it off, upgrade the glasses, upgrade software, and the implant be as simple as possible so you can work with any hardware outside. As soon as you start implanting something in the eye, first of all, it comes with limitations of, say, thermal limitations, how you deliver power and so on, what this camera can do. And then it becomes very invasive. And so I don't think that we want to go this way. There is a benefit of not having glasses at all. That, yes, if you can avoid using glasses and have something that operates under ambient light, that would be ideal. But that, unfortunately, ambient light is very weak for direct conversion of light into current for stimulation, so you need power supply. And if you start with power supply, then it's completely different design. You need to deliver power. You then need to see if your camera is in the eye, it has very limited capabilities of image processing, enhancement, and then, it comes with a lot of limitations. So we have chosen this set of limitations, external camera and external electronics and the simple implant. But some people try to do it other way around, have complex implant, but very limited abilities of processing and upgrade and so on. And in our case, it's working fine. Others didn't succeed so far, but never say never. Maybe there will be an implant that will do, well under ambient light implanted, but we didn't do it, and I don't think we are moving in that direction.
Mr. Gula.
Hi, very exciting work. I just have a naive question. Maybe you answered it before, but when you have a camera that's relays the signal to the RGCs and you have a peripheral vision, does it create a delay in what they see versus the, maybe it's a fraction, but does it cause any confusion to the patient?
Yeah, so that's a good question. We want to make sure that all the image processing we do is fast enough so it doesn't create a perceptual delay, because that would be catastrophic, because you have normal vision that delivers at its normal rate. And then if your other feed would be delayed, it would create this disconnect. So certainly all the image processing should be done within one frame, which is about 32 milliseconds, so you don't create perceptual delay.
Okay, Grażyna is the final person who will ask you a question, and let's go.
Thank you so much. This was such an inspiring presentation. And my question was whether in rats, in your experiments in rats, did you see any impact on the circadian rhythm?
don't know if we didn't look into that. They live, you know, in an animal facility with half a day lights on, half a day lights off, and so I don't know if there is any effect. They are not sensitive to ambient light. These implants don't respond to ambient light. So if they are in a room with lights on, first of all, it's quite dim light on the retina already, but it will slightly polarize the diode. The electrodes will charge up and current will stop. So there will be no stimulation. To provide stimulation, you need pulsed, intense stimulation that will inject charge and that will discharge, inject charge and discharge. If you don't do it, if you just provide light, it will inject a little bit of current, charge up electrodes, the current will stop, and that will be the end of it. They will be unaware that there is an implant and it's doing something. They won't see any response under constant lighting.
So one could think that there is not enough signal to provide circadian entrainment. So they might be losing the light for that.
I don't think there will be any change in their, they are not sensitive to ambient lighting with this implant, and I don't think there will be any change in their perception of light and darkness.
Okay, thank you so much.
Unless it is pulse stimulation by glasses.
Daniel, thank you again. Great progress since last time, and we will check on you a few years from now for really revolutionary changes in those implants.
Thank you very much for the opportunity to share the results. You have excellent seminar. I very often attend. It's really a pleasure. Thank you for running it.
Thank you. Hey guys, one moment.